Previously, we have talked about proof of work, the consensus mechanism that allows Bitcoin to reach a common understanding on the current state of the ledger. Now, it turns out that proof of work is only one example of these consensus mechanisms, and that other blockchains use completely different ones. And even though we can obviously not tackle all of them in this course, and we can only give you a really high-level overview, I still want to show you some alternatives, namely proof of stake and proof of authority. All right, let's get started. Now, first, let us have a look at the definition of a blockchain once again. And this is really important to understand before we go into the actual consensus mechanisms. And a blockchain really is a chain of transactions and states. So you have these individual blocks that are in a clear sequence, and each of these blocks contains updates. And then when you have this sequence, then you can recompute the exact state of this blockchain. So you have the exact state of this database. And these updates or transactions to states, they're both in compliance with an explicit rule set, and this rule set is attested by a reliable network of record-keeping nodes. Okay, so the idea really is that you have some agents in this network, and this may or may not be open, this job, that you have some agents that basically attest that the current state really is in accordance with the rule of this network. And of course, there is a big difference between having something attested and just claiming that something is true without having any proof of it, without having anyone else who is believing in it. For example, when you take your account statement, basically you get an account statement from your bank as just a random example, then this is the state that got attested by the bank. And the bank in this example happens to be the consensus relevant node, because they are basically saying in a monopoly consensus system, they are saying this is the current state. Now in such a system, when you're just adding some zeros to your account statement, it's not going to change anything. I mean, you can do that on your paper slip. Nobody will care. So similarly, in a blockchain system, when you're just changing your local copy of the blockchain, no one will care. You really need to be in accordance with the rules of everyone else, and only when it gets attested by everyone else, only when everyone is in agreement, only then it will be accepted by the network. And of course, and this is quite obvious, the value of the chain, and in particular of the native protocol asset of this chain, depends on the network attesting it. So it depends on the consensus relevant nodes and the consensus relevant resources. If and only if people cross this chain, if they believe that the consensus can be reached in accordance with these rules, and there is a clear set of rules that actually make sense, only then there will be some value added to these assets that are part of this particular blockchain. Now, there are various measures that are supporting consensus or consensus finding, things that you need in order to be able to reach a consensus. And number one is really the explicit and unambiguous rule set. It's really important that everyone knows exactly what these rules consist of, but then being able to create blocks to create new transactions in accordance with this rule set. If people have a different understanding of these rules, then we're back in the fork scenarios that we have looked at last time, which are of course really bad for reaching consensus. So if you have an explicit and unambiguous rule set, then you will be able to detect invalid blocks, invalid transactions easily and unambiguously, and just discard them as if they never happened, not accepting blocks that contain them. And the second one is the decision mechanism. Decision mechanism for consensus over time, so that there are, you know, how legitimate extensions are getting added, also how potentially the consensus in the system can be changed. So when there are legitimate upgrades, let's say, for whatever reason, maybe something is broken, maybe there needs to be an emergency update, you need some protocol of how we can deal with that. And of course, in case of some of these non-persistent forks, so for example a block race, you need a protocol that swiftly resolves the situation and swiftly removes the uncertainty from the system. And then last but not least, you need an incentive system, and that is really important, Usually when you have a more centralized consensus system, then of course you can have exogenous incentives. For example, you could say this person has all the data, this person has other advantages from maintaining the ledger. And it is also protected because only one person has access to a centralized ledger. But as soon as you make it open, you have two issues. Number one is you must be able to verify everything, because you have to assume that people will try to cheat. And number two, you have to set incentives accordingly that people actually contribute resources. If you don't have any incentives, if you don't have any reward, let's say, in a system, then people will simply not provide their computational resources. They will simply not provide anything to the system, any consensus relevant resources, and that would be really bad, because at that point you would really find yourself in a free rider problem, where at the end of the day everyone wants the ledger to be created, everyone wants the ledger to be extended, but nobody actually wants to expend resources to do so. And that's why you also need the incentive system. So to quickly recap, you need the rule set, an explicit and unambiguous rule set. You need the decision mechanism when there is some uncertainty, when there are some changes required. And of course also you need an incentive system that allows people to get compensated when they're contributing towards the consensus. So there are many different consensus mechanisms. In fact, especially in computer science, this has been a research branch for quite some time. I mean, when you look at it, computer scientists, they have been looking into this way before Bitcoin. Basically decentralized computing, decentralized consensus finding, decentralized consensus mechanisms. These are all things that that computer scientists have been interested long before the emergence of Bitcoin. And essentially, when we talk about consensus mechanisms these days, we talk about this trilemma. There are these three goals that you usually have. Number one is, let's go with this one, security. So of course, when you're creating a ledger like that, when you're creating a consensus mechanism with the goal to maintain a ledger, then it's better secure. If it's not secure, you have a problem. That's probably one of the basic properties you always want to achieve. Number two is scalability. That is really important, because when you want to build something like, let's say, a payment system or just something of global scale, and usually it's really important that it is scalable, that you have a high transaction throughput, and that when there is high demand for this ledger, for the use cases of this ledger, that you can actually satisfy this demand. And then of course decentralization, and this depends on the application. But the idea is that, of course, when something is heavily centralized, then you may run into some issues, some of which we have already discussed in this class, like monopoly rent extraction, like a single point of failure, a single point of attack, some malicious centralized agents. There are many drawbacks that are potentially really bad, including also the fact that you will need a lot of audits, that you have a lot of regulation. In that way, also decentralization is a third potential goal. And as a matter of fact, there are, of course, some trade-offs between the three of them, depending on what you're looking for, depending on what exactly you want to build in terms of the system. You can go with either two of them, but it's usually not feasible to also reach the third one. So, for example, you could go with something that is scalable and secure, but not decentralized. You could go with something that is secure and decentralized, but not necessarily scalable, at least not on the base layer, on layer one. Then you need to be much more creative on additional layers, and so on. Now, to be fair, of course, something that is scalable and decentralized but not secure probably isn't that appealing. I mean, as I said, security is the base property you always want. If it's not secure, if people can simply cheat, then the ledger doesn't make too much sense. So the most popular consensus mechanisms people usually talk about are proof of work, proof of stake, and proof of authority, at least in the blockchain space, and there are many variations of that. I mean, this is really just a high-level overview where we briefly tackle these basic consensus mechanisms, but you have to be aware that there are, especially the proof of stake one, there are there's an unbelievable amount of variations, and it gets much more complicated than what we're going to tackle today. This is really just an introduction, and we will look into this proof of stake in one of the master level classes that hopefully we will be able to upload in one of the following semesters, in the context of Ethereum, that is. But for now, I just want to give you a quick overview with the idea that you have an understanding that there are alternatives to proof of work, depending on your needs, depending on how decentralized the system must be, and so on. Now, when we look at these three protocols. I mean, let me first give you just some very, very high level idea what it actually is. I mean, you know proof of work, you know that there are computational resources employed, that the miners, they are recreating these hash values until they find a hash value for a block header that is below a certain threshold. That is the idea of proof of work, and the idea how you can slow down this block creation process. We talked extensively about that one. And then one alternative would be proof of stake. Proof of stake does not employ any computational resources. Instead, what it's doing is you're taking the native protocol asset, which is, for example, Ether in the case of Ethereum, or would be Bitcoin in the case of the Bitcoin blockchain. And with proof of stake, the idea is that you're locking these assets up, so you're staking them, and then you get a proportional amount of lottery tickets, basically voting rights on the next few blocks. We will look into that in a little more detail later on, but that's the basic idea. Instead of getting lottery tickets or voting rights in proportion to your computational resources, you get it in proportion to your stakes, so in proportion to what you have staked, what you have locked up in terms of native protocol assets. And proof of authority essentially resembles just a regular database. It's not that spectacular. The idea is that you have a predefined set of people, or just someone who decides on the current state of the ledger and can exclusively maintain the ledger. And of course, this is heavily centralized. So in this case, it's really not decentralized anymore. In this case, you're much closer to a traditional database that you already happen to know. Now, when you look at a small comparison right here of these consensus mechanisms, then you can talk about nodes or resources. And the idea with nodes really is, do we have predetermined restrictions? So do we have a certain set, a closed set of people that can contribute towards consensus? So do we have a pre-selection of nodes that can actually do that? Or is it, as in the case with proof of work, completely open? And in terms of resources, it means, is there a limited set of resources? And this becomes much clearer when we talk about proof of stake. Or is the set completely open, so there could be an infinite amount of resources employed in this consensus making process? Now let me actually show you all three examples. With proof of work, my laser pointer just disappeared. Here it is again. With proof of work, you have an open set of nodes. So literally anyone can contribute when they're contributing computational resources. So there are no restrictions, no ex ante restrictions whatsoever. And also in terms of resources, since it's computational resources, so exogenous resources, resources that are not internal but external to the system, it's also potentially open, so there can be an infinite amount of resources. With proof of stake, it's also heavily decentralized in the sense that anyone can contribute towards consensus finding by locking up their consensus, by locking up their native protocol assets. This is of course open because anyone can do so, but the resources is a closed set. Why is that the case? Because here we're really talking about endogenous consensus relevant resources, the native protocol asset. There is just a certain number of native protocol assets at every single point in time. So for example, with Ether, there is a certain amount of Ether. With Ethereum, there's a certain amount of Ether at every point in time. And when we're talking about proof of stake, then of course only these Ether can be used as consensus relevant resources. And that's a big difference to proof of work, where essentially somebody could add additional computational resources from outside, and it's potentially completely open, an infinite amount of resources. With proof of stake, this is closed. So proof of stake really is open in terms of the nodes, in terms of the participants, but closed in terms of the resources. And when we talk about proof of authority, then first of all, it's closed in terms of the nodes, because there is a predefined whitelist. You know exactly who is allowed to contribute towards the consensus, but also, of course, they have a specific amount of voting rights, which also is closed because you cannot add additional voting rights, at least not with an agreement among these people. So this would be closed. Okay, so when you think about these three consensus protocols on a very high level, you can think of proof of work as open in terms of nodes, resources, proof of stake open closed in terms of nodes and resources, and proof of authority as closed in terms of nodes and resources. Now, we have already talked about proof of work, so we have some understanding of how it works. I mean, we looked into it quite extensively, but now let's quickly look into the trilemma of proof of work. Again, trilemma in terms of scalability, decentralization, and security. And in terms of scalability, it has its issues, at least on the base layer. I mean, you can always scale on layer 2, and we will look into that later in this class. But the two things is, number one, that every full node needs to process every transaction, the validation, which is for some applications a really good thing because they can validate everything. But the second thing is that the block creation is very resource intensive, and that is in fact exclusive to proof of work. Recall that we had to slow down the block creation process in order to be able to exchange the information. And we did that by requiring a hash value of the block header that is below a certain threshold. And by that, essentially what you're doing is just recomputing these hash values until the entire network, independently of how many resources are actually employed, finds a solution on average every 10 minutes. And this is, of course, somewhat problematic because it uses up a lot of energy when the blockchain is as successful as the Bitcoin blockchain is. And Bitcoin has received its share of criticism for that. Unfortunately, in many cases, people fail to actually look at both sides and look at the pros and cons. Yes, it employs a lot of resources, but many of the statements that you usually read in the media, like there are this much resources by transaction and each transaction consumes so many resources, are completely wrong, don't make any sense, and just witness that many of the people that actually write about it fail to understand the system, which is a bummer. But that being said, of course, and that's a fact, Bitcoin does use a lot of energy, and that is a disadvantage of this system. I mean, it adds, I wouldn't call it wasted, as many people do. It adds to security. It is an important factor of decentralization. But we have to be aware that it is a certain disadvantage because it does use a lot of energy. But in terms of decentralization, that's actually really great properties. Proof of work is an open network with many participants. It is relatively good distributed, relatively well distributed, but there is some risk that the mining pools that we have also talked about undermine decentralization to some extent. Luckily, there seems to be a move back from these really gigantic mining hubs, and mining seems to become more global as we speak, but still there are some dominant players in the system, and it's a highly professionalized business. It's not as it was originally planned that just everyone who is running Bitcoin contributes towards the system on his or her own computer with a CPU or graphics card. It's a highly specialized business with ASICs, so special chips in gigantic server rooms, in gigantic basically factories where they are just have these ASICs hooked up, and the only thing they are doing is really computing these hash values. Now, one more thing you have to consider is when people show you these pie charts with the mining pools, they usually fail to mention or to acknowledge that these mining pools, of course, have a certain influence, but that behind these mining pools, you usually have a lot of different people that are contributing resources to the mining pool. And of course, these people, they could easily switch to a different mining pool. So it's not that when you're seeing a pie chart where a large proportion of this pie chart in terms of the computational resources is actually provided by one mining pool, doesn't mean that this is a single entity. It can actually be a lot of people, a lot of different people that are providing resources to the mining pool. And in terms of security, it is secured by the resource allocation. One big advantage of proof of work is its simplicity. Of course, from a game theoretic point of view, it's much more likely that you have attack vectors, that you have additional attack vectors. When the system becomes really complex, as for example with certain proof of stake implementations, as when you have something as simple as proof of work. So again, as you can see, I mean, there are some advantages, some disadvantages, as with all of these consensus protocols we are going to talk about. So next up we have proof of stake. And proof of stake, in order to participate, you need to provide some resources. So basically each node, in this case called validator, needs to deposit and lock native protocol assets. And when you're locking these up, when you're basically adding them as collateral to the system, where you can also get punished or so-called slashed, then this is called your stake. And that's where the naming proof of stake actually comes from you depositing your native protocol assets as a stake, as a collateral, in order to get some say in the system, in order to be able to create new blocks. Now the block creation and transaction validation, the way it works is that the block creators, they are selected at random in proportion to their stake. So the more native protocol assets you have locked up, the higher your probability of getting selected, that you can propose a new block. And a subset of the other validators will then attest to the validity of the created blocks. So similarly to what we have seen in proof of work, other people will be able to validate the transactions, will be able to validate the state. In this case, it's not everyone. In this case, it's really a subset. They get selected and they also may be rewarded for their attestation. Now, when people are malicious or unresponsive, that is actually one of the advantages of proof of stake, then you can punish them. That is not necessarily, at least not to that extent, possible with proof of work. With proof of work, you could, of course, they can lose their future rewards, but they have nothing at stake in terms of collateral. And with proof of stake, what you're doing is basically when they behave maliciously, when they are unresponsive, then they are either forfeiting their rewards, or you may even slash them, meaning taking away or destroying their stake. So they really have, game theoretically speaking, something at stake. They have this collateral, and if somebody can prove that they acted maliciously, that they didn't tell the truth, then this stake may get slashed and they may be punished. And in terms of rewards, the validators receive returns on their stake by performing their duties. These rewards are funded by transaction costs and or newly generated assets, native protocol assets, that is. So that's quite similar to what we've seen in proof of work, but this time, of course, you basically get additional protocol assets when you're locking up your protocol assets and when you're validating. Now, in terms of the trilemma, once again, it is slightly more scalable than proof of work. Only a subset of validators need to process each transaction, and they have this random proposer selection depending on additional measures that are part of the system. This may become much more scalable, actually. So still, that's probably one of the weaknesses of proof of stake compared to more centralized systems. But again, I mean, the base layer 1, so the actual blockchain itself, doesn't need to be extremely scalable as long as you have patented layer 2 solutions that are built on top of it. In terms of decentralization, it is a no open network, once again, with many participants. So it has great decentralization properties from that point of view. There is one issue, and that is the potential for a crowding out effect over time. So when you think about it, when people that already have a lot of protocol assets, they're locking them up, and then they get additional native protocol assets for their stake, for their action when they are contributing towards consensus, then they may get a higher and higher and higher relative stake in the system, which of course may be bad in terms of decentralization at some point. So to phrase it a little more easily, there is a certain risk that the rich just get richer and richer and richer in terms of the native protocol asset, and that they have a higher and higher and higher say in the system. But also, of course, I mean, this isn't exclusive to proof of stake. It isn't as direct as with proof of stake, but to some extent this is also true to proof of work. And in terms of security, there is a pro, the attacker must acquire protocol asset. And you think about it, this really has to do with the closed resource set. When you want to attack a proof of work system, then you get computational resources, and you can employ these computational resources on a different blockchain as well. Here with proof of stake, what you're doing is you have to acquire the native protocol asset of this blockchain in order to attack it, because you need this native protocol asset in order to participate in the consensus mechanism. And then, of course, if you succeed in destroying this blockchain, this proof of stake blockchain, then you will lose all of your value, because then the native protocol asset of the destroyed blockchain isn't worth anything anymore. Also, an additional benefit is when you're trying to acquire a lot of these resources, then of course demand will be spiking up, because you have this potential attacker that tries to buy up the market, and this makes each additional resource the attacker is trying to acquire more and more expensive, because it just generates a lot of demand on the open market, and then this of course makes the attack more expensive. The con is the complex design that may introduce new attack vectors. Proof of stake is in fact much more complicated than it sounds at a first, or that it looks at a first glance. There are many things you have to consider. Just one brief example. With proof of work, in the case of a fork, to give you an example, you have the nice property that since these are really exogenous resources in the context of proof of work, the computational resources, people have to decide which of these two forks they are working on. They can only employ the computational resources on one of them, only work on one of these two branches. With proof of stake, when you have a fork, then you have tokens, you have native protocol assets on both of these branches, and if this isn't taken care of by cross punishment, by really somewhat complicated game theoretical mechanisms, then you have to assume that people will stake their native protocol assets on both chains. And this would of course not be a good thing, because then both of these chains would get extended, both of these chains would get longer, and you wouldn't have the effect of coming back to just one of these chains as you have with proof of work. Now, of course, there are solutions to that, as there are to many other issues that proof of stake has. And I think researchers and the Ethereum community did a fantastic job in solving some of these issues in a way that still remains a lot of its decentralization characteristics. But that being said, I mean, the more of these mechanisms you introduce, the more complex it gets from a game theoretical point of view, the larger the potential attack vectors to the system. And that's really the con of proof of stake. I think that there are maybe some attack vectors in there, and it's much more prone to that, to being attacked, than a simple proof of work system that can be analyzed quite easily. Now, I'm not saying proof of work isn't vulnerable at all. I mean, with proof of work, you also have some clear attack vectors, but what I'm saying is that with proof of stake, it's much more likely that there are additional ones we aren't yet aware of, just because of the complexity of the system. And last but not least, proof of authority. As I mentioned, this is quite unspectacular because it closely resembles a traditional database where you just have someone or a certain set of people that are deciding on the current state. So the consensus network consists of a small set of approved nodes, of pre-approved ones with special privileges. Basically, somebody says, okay, this is our set of trusted agents, and they are the validators. They are identified, they have a certain reputation, and they choose the transactions that are getting added to these blocks, and they choose the current state. This is, of course, much more efficient. You don't have to go through any of these decentralized lotteries like the computational resource that are being spent, or the stake you have in proof of stake. Here you just have this predefined set. You choose some people, you trust them, and they are validating, and you're done. Of course, as you will see later on, there are severe drawbacks to that in terms of decentralization, because at that point it's just completely centralized. The way block creation and transaction validation works is that validators are either selected at random or they are alternating. They create and validate these blocks, and other validators that are also part of this small set, they attest to the validity of the created blocks. In extreme cases, it's only one validator, so it's only just one single entity that decides on what actually is part of the block. In less extreme cases, it's a set of people that at least can verify that the other people that are also part of this privileged group told the truth. Malicious and unresponsive validators are punished by exclusion, so they are thrown out of the system, thrown out of the subgroup of these privileged agents, and of course they will tarnish their reputation. And one additional thing you have to understand, since these nodes, they are chosen ex ante and we know their identity, then you can also take, of course, some legal action. And that's a big difference to proof of work and proof of stake. In proof of work and proof of stake, you don't have to disclose your identity. Everyone can simply take part in the system. Here you have this closed set of identified people that are exclusively allowed to contribute towards consensus. And of course, when you know these people and they act maliciously, then you can punish them in court. And in terms of rewards and incentive schemes, block rewards are usually limited to transaction costs, and validators often have external incentives to run their nodes. So, for example, data or just some power over the system. There are many reasons why you might want to do that, but it's usually not the same as with proof of work and proof of stake, where you have a direct monetary compensation. Of course, you also have the transaction cost here, but usually it's much more than that. Now, when we look at the pros and cons, it is highly scalable in terms of the transaction count. Now, you have to be careful, because sometimes people, when they talk about scalability, they also talk about node count, and many of these proof of authority consensus algorithms, or things that are closely resemble proof of authority, they aren't really that scalable in terms of node count, but they are highly scalable in terms of transaction count. Of course, there's a higher ceiling for the validator in terms of the hardware, because you know exactly who is part of this group, and then you can push up the hardware requirements quite easily. Also, when you have this network where you know we only have these, for example, 6 people that are consensus relevant, then you can have special networking conditions between them to ensure that the exchange of information will be quite quickly. You can make sure that they have the computational resources they need to process a lot of these transactions. So it is highly scalable, but of course, I mean, it's not decentralized at all. And this is the biggest drawback of proof of authority. Essentially, you're just going back to a regular database where you pick some people, these people run the database, but it's not decentralized whatsoever. Therefore, as you will see, is not immutable whatsoever. And it leads to one pressing question, and that is, who picks these people? I mean, when you have to define these people ex ante, then you need somebody who is even more powerful than these people themselves. That's the person or the entity or the organization who says, yes, you are a verifier, or no, you are not a verifier. And this introduces all sorts of governance issues, all sorts of governance questions. Also, for example, when you have these enterprise blockchains or these consortia blockchains where there are multiple companies involved, you have a lot of infighting, you have all of these political issues, you have competitors that don't want to join a specific project because some other company is already part of it. Just gets really complicated. And the fact that there are special privileges, the fact that there are people that have some special rights, and the fact that there are people who decide on who gets these special rights and who doesn't, introduces all sorts of problems, and it definitely is neither open nor decentralized. Now, in some cases, this may still be a good solution. I mean, I'm not saying you should never, under no circumstances, use a proof of authority system. I'm also not saying you should never, under no circumstances, use a regular database. I mean, for many applications, regular databases are actually a much better choice than a blockchain. But you have to be aware that you're losing many of the properties that are usually associated with blockchain, for example, the open validation, the immutability, the transparency, as soon as you introduce this consensus mechanism. Because in this case, it's really just somebody or a set of people that decide on the state that can do whatever they want to the blockchain. In terms of security, it's not immutable, with all its pros and cons. I mean, of course, for many applications, it's a bad thing when people can just roll it back. But you also have to be aware that in some applications, it might actually be a good thing that people can roll it back. So you really have to understand what you want to achieve. And you have to understand that in some cases, it might be a good choice when you can trust somebody, when it's not that critical. But in many cases, it's a huge issue when you just rely on a single entity. And as I said, in many cases, this really, even though it may have fancy names and it may be called blockchain, but in many cases, when you go with proof of authority, it's just your average database. And there isn't really that much new, that much different. It's just your average database where one person or a group of people decides on the current state. All right, let's wrap up with some key takeaways. Number one, all consensus algorithms have their pros and cons. I think you really have to understand what you want to achieve first, what you want to do before you pick the blockchain you want to run your application on. And there isn't a one-size-fits-all solution. I mean, when you want to go with something decentralized, then you certainly do not use proof of authority because it is not decentralized at all. But when you have, for example, a trusted party in place already, you don't really care that everyone has to trust this party, but it's really important that you have a high transaction throughput. Then, of course, don't go with proof of work. But what is really important is that you're transparent with the advantages and disadvantages. What I think is a bummer, and this is really, really bad for the space, is that there are people running around that claim that their blockchain is immutable, that their blockchain is transparent, when they are using completely centralized consensus systems, when they're using architectures that don't allow for any transparency or immutability whatsoever. And I mean, it's fine if they want to do that, that's okay, but you have to be honest with yourself and everyone else and know the advantages and disadvantages of your system. And I think that is really, even though I don't think it's on this list, I think that is really the key takeaway of this lecture. Number two, immutability and transparency is not given because you call your project blockchain. It depends on the architecture and in particular on the choice of the consensus mechanism. So it turns out it is actually on this list because that's just what I have explained earlier. And number three, it is possible for blockchains to change the consensus mechanism via a hard fork. We briefly talked about that in the chapter on forks, where I gave you the example that you could, for example, take the Bitcoin network and create your own version of Bitcoin with a different consensus mechanism. Then, of course, the likelihood that other people would accept it would be really, really low, but you could do that. You can essentially just change the consensus mechanism and create a fork of an existing blockchain. Number four, these are just a few high-level examples to give you an overview, and you have to be aware that there are hundreds of variations and other consensus mechanisms out there, and that is really important to understand, and this really just should give you a first impression of what you could use when you're creating your own blockchain, or what you could use when you're creating your own project. All right, so that's it for today. See you next time. Stay curious. See you soon.